So in today's class, we'll discuss about the finite element analysis of vector fields. So basically what you observe is all your fields are vector fields, electric field, magnetic field. So in electrodynamics especially, all the fields are vectors. So it is better to actually go for finite element analysis of vector fields. So that's what we're going to do it. So the idea is you can actually extend the boundary value problem involving vector fields for finite element analysis. You can also do it for vector fields also. And as I've told you, it is very important for the electrodynamic problems because in electrodynamic problems, all are electric field vectors or magnetic field vectors. So let us try to analyze boundary value problem for such kind of vector fields. So let us consider a very general problem. Consider a problem of finding the electric field intensity E. We want to find the electric field intensity E. Once you have electric field, you can always find the magnetic field also. So what we are actually trying to find is the electric field intensity E. Because of impressed electric current density, you are actually giving some impressed electric current density J impressed. This is the current density impressed into the system, and it is impressed into a domain. Let us call that as omega, capital omega. And that domain is actually characterized by material parameters, permittivity epsilon and permeability mu. So obviously, if you want to find electric fields intensity, you always go back to the Maxwell equation. So let us try to analyze Maxwell equations for this particular problem we are considering. So let us write down the Maxwell equation for Maxwell equation. The first Maxwell equation, actually the number actually can be interchanged, but let us just call this first equation as first Maxwell equations. Curl of E is equal to minus j omega mu s. This is one of the Maxwell curl equation. You also have another Maxwell curl equation for the curl of magnetic field. This for the curl of electric field. Curl of magnetic field equal to j omega epsilon E plus j impressed. So here we are giving actually impressed current density. And this is our displacement current density. Let us call this as second equation. You also have two Maxwell equations for the divergence of the electric field and magnetic field. Divergence of the magnetic field is always 0 because we don't have magnetic monopoles. Divergence of the electric field should be equal to rho b here. So rho b is the volume charge density. So in this case, we can actually use the equation of continuity to find the volume charge density. So from the equation of continuity, you know that divergence of electric current density is equal to negative rate of decrease of rho b with respect to time. So del dot j is equal to minus del by del T of rho b. So this, if you consider time harmonic fields, then all the time derivatives will be replaced by j omega. In that case, it becomes minus j omega. So if I want to find rho b for this particular case, when I have a impressed current density, rho b can be found out from the impressed current density as del divergence of j divided by minus j omega. So that's what I have replaced here in the right hand side. So divergence of epsilon E equal to minus 1 by j omega, divergence of j impressed current density. And you also have the boundary condition. So let us try to solve this. First, what I would do is basically I would divide this by 1 by mu r. So if the first equation, if I divide by 1 by mu r, it will be divided in the left hand side as well as in the right hand side also. In the left hand side, it will become 1 by mu r curl of E, but in the right hand side, mu is the magnetic permeability. It's equal to magnetic permeability for the free space and the relative magnetic permeability mu r. So we have divided by mu r. So the right hand side simply becomes minus j omega mu naught h. So you again take the curl of this equation. So that's how you usually get the wave equation from the Maxwell equation. You take the curl of the first equation and put the second equation. So that's what we are doing here also. You take the curl of this equation again, then you get curl of this. In the right hand side, you take the curl of magnetic field. So when you take the curl of magnetic field, you have the second equation where curl of magnetic field is given to you. So curl of magnetic field is j omega epsilon E plus j impressed. This is displacement current, this is the impressed current. So you just substitute this curl of H in the right hand side with the second Maxwell equation. So this is what we are getting. So you can further simplify it. First thing is that what is K naught square? K is the wave number for free space. You can express in terms of material parameter as omega square mu naught epsilon naught. So this first term here actually have omega square mu naught epsilon naught. So you can just replace this by K naught square. So this is what we have here. Left hand side remains as it is. Right hand side I have just replaced this term by K naught square. I still have this term. Even this term also I can represent in terms of K naught. You know that Z naught is square root of mu naught by epsilon naught. This is the intrinsic impedance for the free space Z naught. We usually denote it by eta naught, so I'll just denote it by Z naught here. Is the intrinsic impedance for the free space equal to square root of mu naught by epsilon naught. So when you multiply J naught and K naught is what? Omega is square root of mu naught epsilon naught, and Z naught is square root of mu naught by epsilon naught. So what you are getting is Z naught K naught is simply omega mu naught. So this is what you have here in the right hand side. So I can replace this omega mu naught by Z naught K naught. So in that case, this wave equation simply becomes curl of 1 by mu r curl of E minus, you can take this to the left hand side, minus K naught square epsilon R E equal to right hand side what you have now minus J Z naught K naught J impress. This is the wave equation we are actually trying to solve. And this for this wave equation, so in most of the cases in the variational method for the finite element analysis, what we do is we actually find an equivalent problem, which is actually called functional. So the functional for this wave equation we have just considered now is already derived in this book. This is a classic book on finite element methods in electromagnetics by J.M. Jin, professor in UIUC. He's a very famous person in this area. So you can actually refer to this book. We can derive this. This is a functional for the wave equation we have just considered. So first time you have curl of curl. So you have curl of E dot product with curl of E. Second time you have K naught square epsilon naught E dot E plus last term here E dot J. So you have this is very much related. You have three terms here also. After finding the functional, you have first term, second term, then third term, corresponding to the wave equation which has three terms. So if we consider the source-free wave equation, most of the time we actually consider source-free wave equation because we want to find, let's say, wave in the free space. In that case, this wave equation here, this wave equation has the right-hand side here. This impressed current density, we are not giving anything in the free space. Free space, you cannot give any current density. So this right-hand side terms become zero. Our wave equation is actually becomes a homogeneous wave equation. Right-hand side is zero. So if you want to find a functional for this kind of source-free vector wave equation, then the functional is actually will have only two terms here, this first term and second term here. So much more simplification from the previous case. And this is what we actually want to find. One thing to be noted here is we are still considering everything in vector. So the wave equation is vector, functional is also vector. So vector-based functional. So this functional is actually based on the vector wave equation we have here. So let us try to analyze further by taking one particular example. So anyway, this wave equation, when we solve it, we'll get eigenvalues and eigenvectors. So eigenvalues will actually give me this ki here, and eigenvectors will give me ei here. So this will give me different modes inside the waveguide, and we've considered t modes, so we'll get different t modes inside the waveguide. So this will give me the fields for different modes, t modes inside the waveguide. So let us try to do a simple analysis for the high frequency variational function. See, basically we want to actually analyze it for the waveguide T modes and TM modes. So here we'll consider T modes. So let us consider a 2D variational function analysis of a homogeneous waveguide. So actually inside the waveguide you can have different layers of dielectric, fill it up with different dielectrics, then you will not get pure T and TM modes, you'll get hybrid mode. But here we are considering is a homogeneously filled waveguide. That means material inside the waveguide can be hollow or it can be filled up with one dielectric material. So everything material parameter is homogeneous inside the waveguide. So in that case, we can actually have T and TM modes. If we have fill up with inhomogeneous material inside the waveguide, when you fill up with 2-3 dielectric layers, then you'll not get T and TM modes, and hybrid of them you'll get. But we are considering simple case, homogeneously filled waveguide, then you can actually have T and TM modes. And obviously this is a waveguide. Waveguide is made of metals, so all the boundaries of the waveguide, or let's say metals, are actually you have the tangential electric field equals to 0, this boundary condition. So this is the boundary condition on the metallic walls of the waveguide. And we know that the functional for this particular case is like this. The only difference you can see here is del has been replaced by del t, E has been replaced by ET, because we are considering 2D analysis of the waveguide. In that case, we are actually considering only the transverse component of the fields. So we are confined in the XY plane. We are not considering the Z axis. So in that case, del T would be purely in the XY plane. ET will also be in the XY plane. So in that case, if you consider T more than EZ is 0, transverse electric field is perpendicular to the direction of wave propagation. Here we are considering, usually we consider wave propagation as along the z-axis. In that case, Ez would be 0. Then the solution would be of this form, something like Se is equal to k squared Te. E is the generalized eigenvalue problem, and E is the actual eigenvectors we are finding. So this will actually is a set of eigenvectors we want to find. So then we'll have a solution of something like the Se is equal to k squared Te. So S will be contributed from this curl of Et dot product with curl of Et, and this T will be contributed from here, Et dot Et. So then this equation can be expressed in this matrix form here. But then there's some issue with this, because we also have the prescribed value here. So we have given the boundary condition on the metallic wall is tensor component of the electric field is 0. So we don't need to find the eigenvector on the surface of the metallic walls of the waveguide. So we need to just remove the prescribed nodes. We just need to find it for free nodes. So in order to contribute only from the free nodes or free edges, then we have to have this equation of this form here, SFFs EF k squared TFF EF. How do you get this kind of equations? So this can be obtained from the functional. The functional for this E is actually, you can express this EF EP transpose and SF. So like what you have done for band matrix method, where you actually, in the band matrix method, what you have done is you have numbered the free nodes first and number the prescribed nodes later on. Similar to that, we can actually separate the prescribed nodes and free nodes. Then you differentiate this functional with respect to EF, which is the free nodes eigenvectors. So then apply the condition, that boundary condition is over the prescribed nodes, so electric fields are 0, then you can actually get this relation here. SFF EF is equal to K squared TFF EF. So this is the correct relation we want to solve. Just before that, we actually need to know what is this SFF matrix. We know what is K squared. We need to know what is the TFF matrix. So that is all we need to know in the finite element analysis of the T modes inside the rectangular waveguide. So the following slides will discuss how to find out this S matrix and T matrix. So obviously from the functional expression you have, then S matrix would be having components like this. Double integration over the surface, delta T cross curl of Ni dot product with curl of Nj ds. This was the expression you have in the functional. If you remember it, we have something like curl of Et, curl of Et. So now we'll actually replace this by the, see, basically all the electric field, Et would be replaced by the linear approximation of the vector basis function. So that's what we have discussed in the last class. We actually replace Et over every triangular element by the linear approximation of vector basis function. We have discussed that. So when you do that, these are the vector basis function, Ni and Nj. So this term would be replaced by summation of linear approximation of vector function here also. So what you would have is Sij would be something like curl of Ni dot product with curl of Nj ds. So this is what we are supposed to find. To fill up the S matrix, to fill up the T matrix, we need to actually find something like double integration of Ni dot Nj ds. So this is because of this here, what you have Et dot Et. When you replace this Et and Et by linear approximation of the vector basis element, then you will actually have something like this, Ni dot N ds. So what you observe here is our S matrix and T matrix are actually dependent on the vector interpolation function Ni Nj. So this is a little bit different from what we have observed till now. We never use any any kind of vector basis function till now. So, but then the process is very similar, except that our basis element has been replaced by vector basis element. So interpolation function is vector now. So our Sij, when you calculate, it is totally dependent on the vector basis function here and here. So let us try to find out this. And one point to be noted is for the wave propagating along the z-axis, delta t and delta t cross curl of this operator are always in the xy plane. We are confined in the xy plane. So in order to find out this Sij and Tij, let us come back to the simplex coordinate. Simplex coordinate lambda. We have defined lambda 1, lambda 2, and lambda 3. Lambda 1, lambda I is ai plus bix plus ciy. So lambda 1 will become simply a1 b1x c1x c1y, and lambda 2 a2 b2x plus c2y. Lambda 3, this should be lambda 3. Lambda 3 is a3 plus b3x plus c3y. So if I want to express this in a matrix form, then lambda 1, lambda 2, lambda 3 would be equal to b1 c1 a1, b2 c2 a2, b3 c3 a3, x y1. I can write it in a very compact form. And also we know that this lambda I is equal to 1 for node I. So when node I and lambda I, then you have a value of 1, and for other cases it is 0. That is the property of this simplex coordinates. And so because of that property, we can actually find out something like this. So B1, C1, A1, when you multiply with this first column here, what do you get? B1, X1, C1, Y1 plus A1. So that would be actually equal to 1. So that is what you have here. Lambda I equal to 1 for node I. But if I multiply this with this, then it will become 0 for the other node. Second node, it will be 0. First node, this is 1. Second node, it is 0. Third node, it will be 0. That's how you have the set function, right? So when you multiply this with this one, you have 0. Multiply with this, you have 0. But for the second row, when you multiply this with this, it becomes 0. But when you multiply this with this, it becomes 1, then so on. So this is the property of the simplex coordinates. So from there, I can actually find out what are these unknown bi, ci, ai. So if I have the coordinates location for the three nodes of the triangular element, x1, x2, x3, and y1, y2, y3, and 1, 1, 1, or if I have these coordinates x1, y1, x2, y2, x3, y3 for the three coordinates of the triangular element in the xy plane, I can actually find out b1, c1, a1, b2, c2, a2, b3, c3, a3 by using this relation here. So I know what is the simplex coordinate lambda 1, lambda 2, lambda 3 because I know the constant b1, c1, a1, b2, c2, a2, b3, c3, a3. So I know the simplex coordinate. So now then I can always find out this Sij and Tij elements of the S matrix and T matrix. Just before that, let us try to define a very compact notation. Vector Bij is actually gradient of lambda I cross product with the gradient of lambda j. We'll have this kind of terms in the expression for Sij and Tij. That's why we are actually trying to find out what is curl of cross of gradient of lambda I and lambda j. Now that I already know what is lambda I and lambda j, what was lambda I and lambda j? Lambda I was a1 plus bix plus ciy. So when I do gradient of that, I will get bix plus ciy hat. When I do gradient of lambda j, I will get bjx plus cjy hat. When I do cross product of these two, what I get is bicj minus bjciz hat. So this is what I define as bij vector, which is basically cross product of gradient of lambda I and lambda j. And what we observe is it totally dependent on bicj minus bjci. But I can always find out this value of bc from this relation here. Once I know the coordinates for the three locations, three nodes of the triangular element x1, y1, x2, y2, x3, y3, then I can always have this value of bj, cj, or bici. So I can always find out what is this vector matrix bij, which will be required for finding the Sij. I also will need something like phi ij, which is basically dot product of gradient of lambda I, lambda j. What is gradient of lambda I? This is bix hat plus ci y hat. What is gradient of lambda j? bjx hat plus cj y hat. When you do dot product, what you are getting is bi bj plus ci cj. So this is basically giving me phi ij, which is the dot product of the gradient of lambda I and lambda j, and I would require this for finding out the Sij and Tij. So that we'll see like very shortly. Just recall what was this vector element Ni. Ni was actually defined as vector basis function Wi1, I2, and I1 and I2 are endpoints of ASI. You consider one ASI and endpoints are I1 and I2. Basis vector function for that is actually defined something like this. We have considered only first order approximation. We have neglected higher order approximation. It will be simply lambda I1 gradient of lambda I2 minus lambda I2 gradient of lambda I1. This is how I have defined the vector basis function at the in the last class. So what I need is something like curl of Ni. Curl of Ni would be, for example, curl of what is Ni? Ni is lambda I1 gradient of lambda I2 minus lambda I2 gradient of lambda I1. So when this curl operate on this, it will first operate on this first term, then again it will operate on the second term. So curl of lambda I1 gradient of lambda I2 minus curl of lambda I2 gradient of lambda I2. You know from your vector analysis, curl of product of a scalar quantity and vector A, scalar quantity phi and vector A is simply phi curl of A plus gradient of phi cross product with A. And you can see that curl of A is equal to 0. Curl of A is 0. This is one of the vector identity also. When you take curl of a gradient of a so curl of this term, actually we will have this kind of term here also. This one vector identity, you actually it will be equal to 0. So I need to check this equation whether it's correct or not. But we'll have some kind of terms here, which will actually this when you curl operate on this, you'll have first term here, then you'll have second term here. So this first term here, phi curl of A. So this should be a scalar quantity. This should be phi here. So this equation needs to be corrected. Curl of gradient of a scalar quantity should be equal to 0. So when curl of, you take it, it will give you two terms, first term and second term. So this first term would be equal to 0 because it's curl of a gradient of a scalar quantity. Then you will have only this second term here for both of them, and it turns out to be equal. So curl of Ni would be equal to 2 times gradient of lambda I1 curl of cross product with gradient of lambda I2. So if you look closely, this is what we have defined as Bi1, Bi2. Just now we have defined in previous slide. So curl of Ni simply turns out to be 2 times Bi1, Bi2. So now we can find it out. So what we have is Sij is double integration curl of Ni dot product with curl of Nj. Curl of Ni would be Bi1, Bi2, and curl of Nj would be Bj1, Bj2. You do the dot product of these two, but this dot product would be actually independent of the surface area element here. So when you do the integration of this surface element area over the whole surface, you just get the area of this triangle element you're considering. So this will simply become 4a. This is independent of integration. You can take it outside. So this is what we have. So you can actually find out Sij like this. Sij is 4a Bi1 Bi2 dot product with Bj1 Bj2, where A is the area of the triangular element. So area of the triangular element would be negative or positive depending on whether you have done the node numbering is in the clockwise or anti-clockwise direction. That's why I have defined this A as modulus of A ds, where A ds is the area of the triangular element you have considered. Depending on whether you have done the numbering in clockwise or anti-clockwise, this area is going to be positive or negative. That's why we have taken a modulus sign here. So Sij would be simply 4 times area of the triangular element, then dot product of Bi1 and Bj1, Bj2. So we have got Sij. We also want to find what is the other one? Tij. For the Tij, we'll have terms like Ni dot product with Nj. This is the expression for Ni. This is the expression for Nj. So when you do the dot product, you'll have this is the dot product of this and this. You'll have how many terms? You'll have 4 terms here. Dot product of this with this, this with this, this with this, this with this. So you'll have 4 terms here. So we also have a very compact notation of del I2 dot del J2 is simply phi I2 J2. We have done that. Phi is the notation for this kind of dot product of gradient of lambda I2 dot gradient of lambda J2 is phi I2 J2. Similarly, you can also replace this by phi I2 J1. Here phi I1 J2, then last one is actually phi I1 J1. So this is a very compact notation. So if you want to find Tij is integration of Ni dot Nj. Ni dot Nj will have 4 terms here. This is what we have here. So when you integrate it, what you get it. So if you want to find Tij, you have to integrate these 4 terms here. And you can observe that this phi I2 comma J2 is independent of this surface area element. You can take it outside. All the 5 terms can be taken outside. Then you have to do the integration of this. This integration is actually denoted by Mij, and this actually given in the dv division books. The expression is given in the dv division books. Then finally Tij can be found out like this. So this is what we have for the vector finite element analysis 2D case. This is what I wanted to discuss.